Now we'll go with the mathematical modeling of speed governor. Already we have completed the theoretical explanation and animated video, how we have observed how it is working and how the linkage mechanism is working, how the valve of that speed governor vary with respect to the speed changer position settings. Everything we have observed. So whatever we have observed, we are trying to write in terms of equations, right? So before going with the observations, just we have to assume certain points. First point is the system is at steady state condition. That means you have to assume there is no change in demand. As there is no change in demand, the speed changer position setting need not be changed, so that the linkage mechanism will be at standstill condition. That means at stationary condition. So whenever you assume that steady state, the pilot valve is closed, and you have to assume that pilot valve in the hydraulic amplifier is closed and steam valve is open. See, here this is pilot valve and steam valve, this is the steam valve. You are assuming a steam valve is open for certain magnitude. It is a constant magnitude. That means as I am assuming that it is a standstill condition, so it is open at standstill magnitude, right? So there is no change in that. Next point, next assumption is the turbine output balances the generator output. That means whatever the demand is present in that particular system, that demand is satisfied with respect to turbine, so that the generator is also satisfying the demand, right? So everything is in proportion, so that the frequency is maintained as F. Now, so these 3 points are assumption. Now you assume that there is a change in demand. So you assume either the demand is increased. Whenever the demand is increased, the generator output should also be increased. That means delta PG should also be increased. So if I want to increase this delta PGC, the steam input to the turbine should be increases. So if I want to increase the steam input, so I have to control this valve position. See, this valve is connected to which point of the linkage mechanism? E point. So the initial condition was XE naught. So whenever the position is changed according to the variation of the inputs or according to the variation of the demand, that XE value will also change. So that change I am assuming it as a delta E. So if I am assuming this as a delta E, this delta E is taking place with respect to change in A itself. If A point is not changing, corresponding B, C, D, E value will not change. So as E is changing a position, this position change is mainly depends on the position A. This position A is nothing but the speed changer position. If A changes, then only E changes. So everything is mainly depending on the speed changer position. So we have to start it from the speed changer position. So whenever the speed changer position delta XA changes, so delta XE changes, and so on, speed changer position power will also change. So as this A changes, the input power will also change. The input power is, I am considering as speed changer power delta PC. So that with respect to this, what I can say, the delta as delta XA, that means XA was a standstill condition. So it is taking a new value. So change in the two values, previous and present value, is nothing but delta XA. This value changes the change in power also. So here I am taking the proportionality. See, delta XA is directly proportional to delta PC. So that I can write it as delta XA is equal to K2 into delta PC. Here we have to write it as 2. Just you make it note. It is 2. Where K2 is a constant. Where K2 is a constant. Just remember this. The change in speed changer position setting will create a change in input power, and both are in proportion to each other. So delta XA is directly proportional to delta PC. So if I am removing the proportion, so I can write it as a proportionality constant. So delta XA is equal to K2 into delta PC. Just I am writing K2, I am taking K1 as other value. Just there is no